Good afternoon. This video accompanies the development report for the DC to DC buck converter by Connor Seiler. What you see before you is the open loop preliminary design. By running this command here, I shall have to simulate this quickly. Let's go from 0 to 1. Running this simulation, whoops, that was rusty. Running this simulation, we see the transient and steady state response of the DC to DC buck converter. There are 9 traces being ran, representing an output of 5 to 45 volts desired from the 50 volt input. This is done by modulating the pulse source from this one here, from a duty cycle of 0.1 to 0.9 respectively. When this shall run here, I shall show you the average voltages and adjust the graph to show how close they are to the desired output. This is the final trace now. By adjusting this down here from 50 to, as you can see, they are all very, very close to the desired levels, 5, 10, etc. up to 45. Because of the transient state here, the efficiency is going to be quite a little bit decreased, as this section of the thing is usually ignored. If the converter is ran for 5 minutes, 300 microseconds of time is going to be negligible. But as we can see here via the SPICE error log, the efficiency is roughly from about 60 to 95%, with the highest efficiency being ran at the highest duty cycle things. If I was to decrease the time it was running, it would increase dramatically, as is demonstrated in my report. Sorry, I also have a separate different design, this one here. This is the control loop design with the closed circuit feedback. This design here is run solely by this power source, which is the set point from 1 to 5, 1 representing 10 volts and 5 representing 50 volts. This circuit works in a very similar way to the this one here, with the added feedback coming out of the back of the Vout and replacing the voltage source here. It works via negative feedback using a differential amplifier and then amplifying the difference between the desired input reference voltage and the actual voltage coming out. And this goes through P control and I control, which are summed together and used to drive the MOSFET using the MOSFET driver. I need to check my simulation command to see which one I have here. If I do param, if I change this one to the active thing, this will step the input reference voltage from 1 to 4 volts to give you a 10 to 40 volt output. Should not take too long, and we'll be able to see that running in a second. There we go. This works in a very similar way to the other one, except this one has a slight overshoot to it due to the closed loop nature of the design. I'll shorten the simulation time slightly because it is rather long. I'll go to 0.3. Yeah. Right. So there should be 4 things here. Now, whilst this simulates, I'll explain a couple pieces of knowledge I've acquired over this design process. Right, so for the closed loop system, it's very similar to the open loop, except I am experiencing some steady state error, a little bit of overshoot. The overshoot is not massive, as you can see. It's about maybe 1 or 2 volts, and I have done quite a lot of work to reduce this in the PI system here. The steady state error reduces the closer it is to the 25 volt midpoint and increases slightly towards the ends. We'll just wait for this second one to finish up, and I will finish my recording. The circuit is cooled via a heatsink, which is not technically required if you're reading my report, but it's nice to have one anyway, just to make sure. Yeah, and there we go. This is the last trace coming in, of which I will scale once it's finished. Very good. Right, if we change this from 50 down to, do that again. Yeah, as you can see, they are reasonably close to the desired outputs. This one is about 12 volts, which is about 2 volts over, and this one is 38.5, which is 1.5 below, except these two are reasonably on point. Yeah, you'll see these circuits in the report. Thank you very much for watching, and I hope you have a good afternoon.